Hi everyone, my name's Edwin. Thanks for coming along to my talk. What I'd like to do in today's talk is just show you a few of the new things that we've been working on in our new version of Idris. So Idris, if you haven't seen it before, Idris is a functional programming language. It's built on, as a result of decades of research by all kinds of people into type theory. And in particular, the new version of Idris that we've been working pretty actively on over the last couple of years is built on a new type theory called Quantitative Type Theory, developed by Conor McBride and Bob Atkey. And I'll say a bit about what that means over the course of the talk. So we'll see some of the features that gives us. But if you've been to one of my talks before, you probably know that what I like to do is rather than talk about stuff, I like to actually demonstrate them and show you how you might use things in action. So for that, it does rather require having Idris 2 installed, which sadly currently I don't. And just from from the realms of things I wouldn't dream of doing in a live talk. And really just to show you that it's not a huge burden to get Idris 2 up and running on your own machine. Just to show you what you need to do. So assuming you've got hold of the source from GitHub, then I'm assuming you have a Shea scheme compiler available. So that is the dependency that we have is Shea scheme. So we can just bootstrap it from some generated scheme sources if we tell it where the scheme compiler is, and just see how long. I'm just going to see how long this takes, and while that's building, I'll continue with the intro. So I do this partly to show to give some kind of feeling for how quickly you can work with Idris these days. So we've made huge improvements on the performance of Idris over Idris 1. But also to show you that it's not really a huge burden to get up and running. It is a relatively simple process. Anyway, Idris is a functional programming language, as I said. It has first-class types. When I talk about first-class types, that means types are just like anything else in the language. So there's no kind of distinction between types and values in terms of what you can store in variables and what you can pass to functions. Also, it supports type-driven development. By that, I mean you start with the type and you interactively work towards a complete program by refinement, by asking the machine questions as you go. So you don't write the whole program and sort of treat the compiler as the oracle or even the teacher that's assessing your work. So you write your whole program, you submit it to the compiler, and if you're anything like me, the compiler just says no with a load of error messages. So I don't think programming should be like that. Programming should be a conversation with the machine. That is, we should be able to write a partial program and ask the machine if it can give us help in writing the rest of the program. So a lot of what we're trying to do with Idris is bring this type-driven development idea up front and very much treats programming as a two-way process between us and the machine. We'll see a lot of that as we go as well as we do the demos. With a dependent type system, or with any kind of expressive type system, what we can do with our function declarations is say exactly what a function is supposed to do. So we can be very precise about what the inputs are and how the outputs relate to the input. If we add a notion of linearity, we can also start saying when it's allowed to do it. So dependent types in particular give us a way of saying what a function is supposed to do. Linear types give us a way of saying when it's allowed to do it. So what are quantitative types? They are, in essence, they're a way of combining linear types and dependent types. So they're a way of combining precision about what we're going to do with precision about when we're allowed to do it. So originally devised by Conor McBride. So there's a very nice paper describing this from Philip Wadler's Festschrift in 2016, Wadlerfest. I got plenty of nothing. And this explains the basic idea behind it. It gives a first description of the type system. It turned out there was a small bug in that type system, which Bob Atke resolved, and then there's a follow-up paper, The Syntax and Semantics of Quantitative Type Theory. Essentially, that is what's implemented inside Idris 2. So the key idea behind it all is that variables are associated with a quantity. Inside any definition, that quantity tells us how that variable can be used, whether it can only be used statically at compile time to reason about things, whether it can be used exactly once for reasoning about protocols, or whether it can be used in an unrestricted way. So there's lots of possible choices we could take for quantities. So essentially, any semi-ring would do. We've decided, at least for the moment, to just make a concrete choice in Idris 2. It's something about, you may have heard of your language strangeness budget. I quite like this concept because it's if you're introducing new features to a language, it's a good idea to only do one at a time and to just hit people with one thing at a time. So rather than being able to abstract over all possible semi-rings, we've just said, we'll make a choice. We have 0 for not used at runtime, we have 1 for used exactly once at runtime, and we have omega, generally, which is the default in Idris. The default is unrestricted usage at runtime. So this allows us to express erasure, this allows us to express linearity. Okay, let's see how that build is doing, and we'll launch into the demo. So, right, it's done. 4 minutes 41 seconds. So that's a little bit of an overhead over what happens when there isn't a video being encoded in the background. There's also I've commented out the running the tests. So we're just going to assume that the test suite passes because it type checks, didn't it? I shouldn't say that sort of thing out loud. And we'll install it, and then hopefully that means everything is good. Great. So ready to get on with the demos. So this first example, this is just a warm-up to give you an idea of what interactive editing is all about. So I've got a type signature here. So type signatures in Idris, or the general syntax of Idris. If you've seen Haskell before, Idris will be reasonably familiar to you. The main thing is a single colon for type declarations, because we think type declarations are important, so we have fewer characters for them. Also, colon is just what types are supposed to be declared with, aren't they? I think so anyway. So to give you an idea of how interactive development works, we start with a type and we ask the machine to just refine the program based on the type we've given. So I'm in Vim here, which has an Idris interaction mode. Other editors have Idris interaction modes. Vim is the one I just happen to work on. So we've got a few options. So we can ask it to add an initial clause for the definition. So it gives us a candidate definition. This thing on the right hand side, we're going to see a lot of these. This is a whole. If you happen to be designing a programming language or working on the implementation of a language with a static type system, I'm almost begging you to add holes. They are incredibly useful because they allow us to ask the machine what is needed at a particular point, and it's particularly useful if they're not like errors or anything, if they just are things that you can compile. So at runtime, this would turn into a runtime error that says I've encountered a hole you haven't implemented yet. But it allows us to run partial programs, and crucially, it allows us to ask the machine about the context. So we can ask the machine, show type here, and it will show us the context. So it'll show us what we had available. So I'll just do that again with the keyboard shortcut. So it says, well, you've got a type, you've got x, which is of that type, and you've got k, which is a natural number. One thing to notice here is the 0 next to the tie variable. So that 0, that's an initial example of a quantity. What it's telling us here is that you can talk about that tie, you can use it for reasoning about the program at compile time, so we can use it for type checking, but you can't have it at runtime. Which is as you'd typically expect of a type, I suppose. Now the 0 quantity really starts to become useful, really starts to show pull its weight when you have more interesting computations at the type level. So I've constructed a small example here. This is the smallest example I could come up with that illustrates some interesting concepts happening at the type level. So we're talking about run length encoded lists. So run length compression is a form of compression where you say you if you have a lot of repetition in your list, so maybe I have 4 x's followed by 5 y's, so that's quicker than saying x x x x y y y y y. The data structure, the key data structure to this is this RLE data structure. So run length encoded data, and I'm only aiming for soundness in the representation here. I'm not aiming for the best possible run length compression, or even necessarily a good run length compression. It's just a sound representation of a run length compressed list. So the empty run length encoded list is a representation of the empty list. So we're saying that run length encoded data is parameterized, or I should say indexed. It's indexed by the list that it's compressing. So the original list is part of the type, and we can read off, by looking at the type, we can read off what the original list was. So we have our friend rep here, which I haven't implemented yet. This is sort of more a teaser for another talk. But one thing that I've been working on quite actively recently is type-driven program synthesis. So if I ask Idris to generate a definition for rep, then it will do a bit of program search, and interestingly, the first implementation it finds is exactly the one we want. When it gets to a complete definition, it won't stop when it just finds the first definition. It will keep looking. Like the simplest definition of this would be to always return the empty list, for example. So rather than stopping when it's found a first definition, it generates a batch. So somewhat arbitrarily, I've picked 16 as a reasonably low round number. So it generates 16 definitions, and then it orders them so that the one that uses all of the variables is the first one you pick. And so that was a heuristic that was suggested to me by Leonard Augustin a couple of months back. So he said that he uses that heuristic in his GIN tool for Haskell. Turned out to be a really good heuristic. Turned out to very often come up with the definition we want. Now the interesting thing in this example, as far as quantities go, having set all that up, is we'll see in this uncompressed function. So I do have the function for compressing, but I won't talk about that today. So the interesting thing is uncompressing. So if we want to uncompress run length encoded structure, so we've got a run length encoded list x's, uncompressing it is going to come out with a list. And in fact, the list it's going to come out with is specifically x's. So we could try writing that definition. I'll do the usual thing of add a definition, and something we could do in Idris 1 would be just, we've got x's available. We've got x's in scope. X's is the input list. But in Idris 1, we might have been tempted to say, oh, well, we'll just use x's. We have the uncompressed list. Let's just use it. Don't think we do want to do that, though, because if we do that, it means that we're kind of carrying around the uncompressed data and the compressed data together. So the fact that we are just directly accessing the uncompressed list means we haven't really achieved anything. In fact, we're taking more memory because we're carrying around the uncompressed and the compressed data. So it's kind of important that this uncompressed list is not available at runtime. And what we really want to do is have a way of saying we're going to reconstruct a list, and the list that we're reconstructing is exactly the list that the compressed data is indexed by. There's a little bit of a hint above. So I've got this single type, so it's like a value-y singleton type, and a singleton type, it's indexed by something, by a value. And it means that the only value that is carried by this type is the one we see in the index. So if I were to say, instead of saying just returning any old list here, if I were to say I'm going to return a singleton list x, I can let me move that now. So we're going to return a singleton list x's. Then that means, well, this list, there's no quantity annotation on it. When there's no quantity annotation, that means it's unrestricted. So these values are unrestricted. That means when I construct the result, I'm going to have some value available. The value is definitely going to be x's, because remember, we're allowed to talk about x's. X's is something that although there's 0 of it at runtime, we are at least allowed to talk about it at compile time. Uncompress is going to be our way of getting something that is available at runtime, that is guaranteed by compile time reasoning to be equivalent to what x would have been had we passed it in directly. And what's kind of fun about this is that we're kind of undoing this RLE function where we're doing by pattern matching on the run length encoded list, where we're going to so in one case we're going to find that it's an empty list, in another case we're going to find that we have n copies of x's, and the program that reconstructs the list is in fact the program we've written in the RLE type. So it's we would hope that, given that we've already written the program once, we don't really want to write it again. So actually I'm going to go to the Idris menu here. I'm going to say generate definition, and by a bit of type-driven program synthesis, it's generated us a program that computes the list of what x's would have been had we had it available at compile time. So the important thing here is quantities are a way of being clear about what exists at compile time and what exists at runtime. So this x's in the run length encoded data, this had better just be something at compile time, because if it's at runtime, we haven't really succeeded in compressing anything. And then the dependent types, the relationship between the input here and the output here, is saying that what this function does is take the explanation of what it is at compile time and turn it into a real thing at runtime. To illustrate linearity, so one quantity, let's take a look at how we might use the type system to encode a resource usage protocol. So as I said earlier, linear types allow us to say when things are allowed to happen. So dependent types for what, linear types for when. So one thing we might want to do is encode a secure data store where the data store, we can only read the secret data from the data store when we've successfully logged in. When we log in, that might fail or succeed depending on whether we got the right password. So we start in the logged out state. We can get into the logged in state if we log in and the machine tells us yes, that succeeded. We can read the secret as long as we're in the logged in state, and we can log out and get back to the logged out state when we're in the logged in state. So we're going to use linear types to say to represent the data store, and think about I mean, there is only one data store, so there is an external resource that is our data store. Every time we do some computation on the data store, every time we sort of we modify it, we've effectively consumed the old version of the data store, and we have a new version of the data store back. So we can never refer to that old one again. So in this way, we can encode a resource usage protocol in the type system. So let's see how we do that in Idris code. So here's a representation of that idea in code. I'll move up a bit. So we've got the two states of the data store, it's either logged out or logged in, and we've got it's just a mock-up. So this is a kind of representation of the store where we're holding the secret. In reality, you'd probably expect this to have maybe a pointer to an external resource. Though in this case, it's just saying it contains the secret data. And we're going to define some top-level operations that manipulate, give access to the store. So the first thing we need to do is connect to the store. So this is probably the trickiest thing that needs a bit of explanation. So quantities are on binders. They're not on types. They're not on return types. They are only on binders. So that means if we want to create something that is guaranteed to be linear, then we need to use a continuation that says in that continuation the store that we're referring to, or the value that we're referring to, is linear. So connect takes a continuation that says it's an I/O program that itself is guaranteed to be run exactly once. So this function from the store to I/O is guaranteed to be run exactly once, and the function itself takes a store. In the body of that function, the store is guaranteed to be used exactly once. So this is like resource bracketing. So we're constructing the store inside the body of the function. The store must be used linearly because it is a linear store, and this is the only place where we're able to construct the store. So provided that we know this is where it's constructed, we know that all stores will be used linearly. That's so it's about putting the right things in the API for that to be true. So we've got 3 transitions on the machine. We've got login, logout, and read secret. Logout is probably the easiest one to look at because it always succeeds. So if we start with a logged in store, that gives us back a logged out store. So every input here, because the store we construct is linear, we can only ever use that in a linear context. We will only ever be able to pass it to functions that consume it linearly, or more restricted. So we won't be able to pass in a store to a function that takes an unrestricted store because we can only ever construct them linearly. So every use of a store is linear, and that means we return a new store state. The type of login is a little bit trickier. I won't say in detail what this res is, except to say that it's a dependent pair. It allows you to return a result and some type depending on that result. And the reason we need that is login doesn't necessarily succeed. We're not in control of the login process as programmers. The machine is in control of that. That is a thing we'll only ever find out at runtime if the password is typed incorrectly. So this will return a boolean that says whether we succeeded or not, and then we calculate the type. So the store we get back is either going to be logged in or logged out, depending on whether this result is true or not. So this B refers to the returned value of the result. So let's just write a little sample program to see how this sort of thing can work. So we'll connect to the store, and in fact it's always worth replacing programs with holes just to see how they're constructed bit by bit. So we'll see at this point the body of the connect function, so the body of the whole operation. We've got a logged out store, and we have to use it exactly once. So we have to run through this protocol. The only way we can get rid of a logged out store is to disconnect. So eventually we're going to disconnect. Otherwise we have to follow the protocol as defined in these types. So let's undo all of that. So if we try logging again, we can see what happens after we've logged in. So this OK hash s, this is a hash is just the constructor of res, so it's a way of pairing up the result and the store. So if we check the type of help now, so we've spent our original store, we have a new store, and the type of that store, well, we don't know yet. We don't know what state it's in. We'll only know what state it's in after we look at the results of whether it succeeded or not. So OK says whether it succeeded or not, and the type here, it's kind of a hint in the type as to what we need to do next. So if we do what it says in this type in the body of our program, then it should refine the type of the store to be either a logged in store or a logged out store. So essentially what we're going to do is in the program we are going to reflect what the protocol says we have to do. The protocol says the type of the store depends on this result, so we will continue by checking that result. So in the case of help 1, we've got a logged in store. In the case of help 2, we've got a logged out store. So we're using holes here. I remember at the beginning I mentioned holes. Holes are really useful for this sort of program because especially as protocols get a bit bigger, you get a lot more. There's a lot more things going on. A lot more possible paths you could take through the protocol. So having holes gives the machine the possibility of telling you where you are in the protocol. So you're not going to make a mistake because you think you're in one branch when you're actually in the other. And you don't have to write the whole protocol implementation up front. You can use the types in the holes to help guide you towards the correct protocol. So let's do this last case first because it's easier. So we're just going to, in fact, that's all it is. It's just, if it didn't work, then we'll disconnect from the store and we're done. Good. And if we did successfully connect to the store, then we'd like to read the secret. So let's read the secret from the current state of the store, and we know we can do that because we just checked in help 1. It's a logged in store. So are we good? Yes, we're good. So what do we have now? Well, we still have a logged in store. So this is, by the way, this is worth mentioning. It's something a little bit annoying with linear. If you've ever programmed with linear types, one of the annoyances is it's useful that you can only use something exactly once, or you have to use something exactly once. But it's also an annoyance because if you're doing something that's really just read only, then you have to return the input back to the function that passed it in. So there's possible ways we could think of dealing with this. So it's maybe just a notational thing. So you might think of something like Rust has borrowing. So you could say, I am lending you the store as long as you promise not to destroy this store. We could just pass it in. Or we can maybe look at some other work that's been done on that. So in Waddler's linear types can change the world, for example, he had an approach to knowing when it was okay to treat something as a read-only reference. So these approaches won't necessarily directly map to the way we do things in Idris, but they are things that we should probably look at just to avoid this annoyance of having to return a value, return the linear value, even when we're just reading it. But for the purpose of working through protocols safely, I think it's bearable. But for larger examples, we might want to think more about making it look nicer. Anyway, so we've read the secret. Let's just print it out, and then we'll log out. So just check that we're still in the right state. It's always good to check at each opportunity. Yes, so we're logged out now, and now we can finish by disconnecting. Great. So we have a correct implementation. We've worked through a full implementation of this store protocol. So this is nice as a way of expressing protocols in types. It means that the things are very safe. It's worth thinking about how that scales up. So we always like to come up with these fancy examples and showing off what our type systems can do. But I think just the day-to-day stuff of giving types, precise types to APIs, where the types give you more hints as to what the function is supposed to do and when it's okay to run a function. I think that could be very valuable just for day-to-day programming work. And one example that I'll briefly look at now, because we're running a bit short of time, is how to give better types to the network socket API and show how linearity can capture that. So imagine we're writing a server using the network socket API to manage connections. So using the standard POSIX sockets API. So what we need to do to achieve that is we create a socket, we bind it to a port, we listen for connections on that port. When a connection arrives on that port, we'll accept the connection. At that point, we have an open socket. So there's quite a few things we need to do here. There's an order of operations we need to follow that is important. These operations could all fail for various reasons, so we need to have some kind of error handling at various points during this operation. So a good place to start is, rather than designing the API directly, think about what states those sockets are going to be in. So we'll think about what the operations are and how they affect socket state. So that is, we'll initially start in the closed state, we bind it to a port. At that point we can start listening for connections. So when we listen for connections, if a connection arrives, then not only do we create a new socket for the communication to happen on, but we can also carry on listening on the current port because we might get multiple connections. So I've kind of represented that in this machine by saying we can go from the listening state to an accept will get us in the open state, and it will also keep us in the listening state. So at each point, or various points in this, it's okay to close the connection. So our API is going to somehow capture these operations and how they affect the socket state. So we'll only be able to do communication on the socket once the socket is open, and we need to close the socket. We need to tidy up after ourselves if there is an error, or if or once the communication is complete. So there's a primitive API. So I don't want to go all the way back to the sockets API here. I'll just show you what the Idris primitives are. So the general approach we take with I/O code in Idris, or what we've done so far, is define the I/O primitives. So this using has I/O, or all that means. So using is a way of saying all of these operations are. They're all using the has I/O interface, so they're all imagine a constraint on the has I/O interface throughout. It's the way of not having to write that every single time. So we abstract over different ways of doing I/O. So I mean it's like monad I/O in Haskell. Essentially, it gives us lots of different. It means you can write I/O operations in lots of different contexts. So we've defined a few primitives. The primitives don't capture anything about how the socket state changes. So the primitives we provide are kind of unsafe, and we'll use linearity, and we use we kind of lift the I/O interface into a linear I/O interface to add a safe linear wrapper for I/O operations. So we're at least capturing that things might go wrong with an either type, and capturing result codes, and we've been precise about where the sockets are. But we're going to use linearity to make a better interface that says not only what these functions do, but when they can do it. And the way we do that is, so instead of has I/O for just ordinary I/O operations, we have we say that this I/O interface has to be a linear variant. That is, so the distinction between ordinary I/O and linear I/O is so in the monad interface, the bind operator isn't explicit about how many times things get run. So it's important when we're chaining I/O operations in a world of linearity. It's important that the first operation is run exactly once and the continuation is run exactly once. Otherwise, well, the technical reason is otherwise it won't type check. So if things are going to be, if an operation is going to be used linear, or a resource is going to be used linearly, it can only be used in a linear context. Ordinarily, if we're just generic in using a monad, monad doesn't tell us that things are being used linearly. So basically means you can't throw an exception. So this L type, again, I won't go into the details of this. I've chosen a short name because I expect it to be used a lot. It's a way of lifting I/O operations into a linear setting. The implicit argument use says how many times we expect the return type, or the return value of this operation to be used. So binding to a socket, or binding a socket to a port, takes a linear socket that's ready to be bound, a couple more parameters, an address and the port to bind it to, and it will give us back, it will be an operation in the linear I/O setting that returns whether we succeeded, and a socket where the type of the socket depends on whether we succeeded or not. This socket that comes out is something that's going to be used exactly once. So the bind operator for this L monad it calculates the type for the continuation based on whether the return value is going to be used once or not. So remember, it's all about continuations. So that we bind the usage of, or the quantity of a variable, it's on the binder rather than on the return type. But we're working in, so L is a monad-like thing. There is a bind operator. The bind operator says what you're going to do next. So I mean, that's our continuation. The binder is, we bind the result of this operation, and that's where the quantity lives. So binding to a port, it returns a pair of a result and a socket, and the socket that's returned has to be used once. Similarly for the other operations, I haven't put the whole API here. They'll pretty much follow this form of saying what the type is when it goes in and how the type is calculated when it goes out. Eventually, when we're finished, we have to consume the socket. So the done operator says, give me a linear socket that's currently closed, and I will give you back an unrestricted unit type. So let's see, just quickly see how this is used. And seeing how it's used, it's following the same sort of structure as we saw in the data store example. So except that we're using do notation rather than let bindings. And again, we can use holes to give some indication of what's going on. So let's replace after we've bound the socket to a port. So something might go wrong. So this alternative, this is a pattern matching alternative notation. So if given that the result of bind could either succeed or fail, we don't want to have hugely nested if then else statements or hugely nested case blocks. So this pattern matching alternative notation gives us a quick way of aborting from a computation. So this is something that Idris has had for a while, and it turns out to be practically very useful if you're using return types to indicate error rather than exceptions. A quick way of aborting a computation. So yeah, we've bound the socket to a port in the happy path. So in the happy path we have a bound socket that we use exactly once, and then in this unhappy path we have a socket that's closed. So what we'll have to do essentially is at that point discard the socket. So we're finished with the socket. But otherwise it's following the same sort of idea of using the state machine in the type to keep track of the socket state, so that if we use the socket operations in the wrong order, it's going to be a compile time error rather than something mystifying going wrong at runtime. Which I don't know about you, but my experience of learning network programming was generally one of mystifying things going on at runtime. So yeah, the what's happened here is we've done a linear version of the sockets API where, in addition to just saying it's a socket, we're explicitly saying what state it's in. We're encoding the state transitions as part of the type. So we've got some idea not only of what these operations do, but when we're allowed to run them. Okay, so I'm basically out of time. I will wrap up there. And as a summary, I've given a few examples of quantitative types. I've shown you the 0 and 1 multiplicities in particular. So these are the interesting new things in Idris 2, in the Idris 2 type system that QTT gives us. Gives us more information in interactive editing because it tells us what we have available and how many of the thing we have available. So using holes certainly helps here. And it's just a little bit more information to give to the type checker about what is coming up. And it means we can think of programming more as a conversation with the machine. We give the machine more information. It gives more information back to us. Together, we will work towards a complete working program. I think the most interesting result in what this enables now is we can start defining protocols as types, just as linear functions, and then implement them directly, interactively, looking at the holes to tell us what comes next, looking at the context to see what state all of our resources are currently in. So rather than writing the whole program and having the machine check it and then testing it to find any protocol violations. We get the protocol correct by construction. Okay, so that's an overview of Idris 2, what's new in Idris 2. Thank you for listening, and I will be around after the talk if anyone has any questions or points for discussion. Thank you.